Thank you. So Søren and I is from Kvantify, and just to introduce ourselves, I'm Stig, and this is Søren. I work as a quantum engineer at Kvantify, and I have an education, a PhD in quantum computers, so I know a lot about them. And Søren is also a physicist, but he has spent the last 10 years doing software, so he will be the expert in the high-performance computing part. All right. So you probably know that computers have done a lot of great things during the last 2 decades or 3 decades. And Moore's laws tell us that every 2 years, the number of transistors is approximately going to be doubled, meaning that we get exponentially faster and faster computers. Unfortunately, it looks like we cannot create faster and faster computers using or following Moore's law anymore, because computers are becoming so small that quantum effects are starting to play a role. And a typical quantum effect is quantum tunneling. And this happens when the barrier between two things is so small that things can go through the barrier instead of going over the barrier. This is a problem when you're doing circuits, because suddenly the current can go through different wires instead of just in the wire you want it to. And this is a problem when you're building small computers, because you don't want that to happen. Then you lose control. So how do we fix that? We could either give up and stop building faster computers. That would be boring. Or we can try to fight this quantum problem. The last solution is, of course, just try to do something cool with this quantum effect instead of fighting it. So that is the solution that we're hoping is the right one, simply to incorporate these quantum effects in computers and start using quantum computers. So I assume most of you are not physicists. I know some people are, but let's just go through a quick course in what quantum mechanics are. So quantum mechanics is what rules the very, very small world. And we're down in atomic level, that's 10 to the minus 9th meter. And back in the days when Niels Bohr was alive, he invented this atomic model where you have a nucleus in the middle, and then you have electrons circling around the nucleus as planets around the sun. It turned out that this wasn't a very good description of most atoms. So instead came the quantum atomic model, which state that the electrons are not well defined in orbits around the nucleus. Instead, they're distributed in some sort of cloud around the nucleus, meaning that they're not at any specific position until you look at them, and then they decide where they are. This is very weird, and if it makes no sense to you, that's perfect, because it should make no sense. Things can be in several positions at once. That is not something that any of us is used to. But we want to use this effect. If things can be at more places at once, then we can do more calculations at once. And that would be really nice. So we want to make this quantum bit instead of a regular bit. You probably know a regular bit, or a classical bit, as we call them. It has a 0 state and a 1 state. It can be in either of those two states, and then we've collect a billion of those and do a lot of calculations. That is basically how a normal computer works, give or take some technical details. In a quantum computer, we want to create a quantum bit or a qubit. A qubit works out of this quantum mechanical principle where it can be more than one thing at a time. It can be in a superposition. So here we have the 0 state and the 1 state, and now we're in a superposition of those two states, and given these two coefficients, alpha and beta, and they can be whatever they are. These are complex numbers. So basically, we're just end up with this linear algebra equation telling us what state our qubit is in, until we look at it, and then it decides, are we in the 1 state or in the 0 state? This means that we can, in principle, do several calculations at the same time, because we can be in both states. But in the end, we can only get one result out. So that is one of the problems that we're dealing with in quantum mechanics and in quantum computing, that we can do all the calculation at once, but in the end, we're only allowed to look at one solution. And once we figure out how to get the right solution out, then we're getting a long way in quantum computing. All right, so how do we make these qubits? There are several different ways to do this, and there aren't any preferred platform yet. So think of this like back in the days in the 1950s, when computers was also very young, and different companies competed about how to build these bits that we use in classical computers. Back then they used vacuum tubes and whatnot to make these bits. So currently there are the superconducting circuits, which, as you probably know, some of these companies, IBM, Google, and Alibaba, is working on these superconducting circuits, and a small company called Rigetti, which is also very good. There are ion traps, where IonQ and Honeywell, which you probably know, is also working on these, and then some other Rydberg atoms, photonics, silicon quantum dots. This is something Intel is doing, and topological qubits, which is a Microsoft preferred platform. I'll go through some of these platforms and talk about what are the pros and cons of those. So superconducting circuits is a prominent platform using very cold chips. So imagine you take a regular computer chips and you supercool it down to minus 273 degrees. That's what is called absolute zero, or at least very close to absolute zero. So it's very, very cold. And at that temperature, things become superconducting, meaning that there are no resistance in the wires. Then these chips, they consist of conductors and inductors, as you know, probably. And then we introduce a nonlinear inductor known as the Josephson junction, which I've depicted here. And that is basically, we take a piece of wire, make a cut in it, such that the current can't go through the insulated piece of wire. But we're in the quantum regime now, so these Cooper pairs, which is basically just two electrons, can tunnel through this insulated barrier. And that is basically our qubits. We can see this as if the Cooper pair is over here, we're in the 0 state, and if it's over here, it is in the 1 state. And since it can tunnel back and forth, it can be in a superposition. So these qubits we can build, IBM has a record building around 400 qubits in this method, and Rigetti and Google and Alibaba has a bit fewer. Actually, I'm not sure about Alibaba. It's a Chinese company, so they might have more. But they're quite fast. They're in the megahertz regime. That is not compared to a classical computer, which is in the gigahertz regime. It's a bit slower, but if we can parallelize in a good way, it might not matter that it's a bit slower. And this is actually a picture of a quantum superconducting circuit where you have the Josephson junction here. So that means that we have 4 qubits here, and then some regular inductors and also some conductance in it. All right. Then there are the trapped ions, which is basically that we take an ion, which is a charged particle, and then we trap it in a magnetic field. This looks like this. In an experiment, and basically you can actually see this if you zoom in. So you have these 7 dots. That is actually ions that are trapped in this magnetic potential. And then because ions are atoms, they're actually already quantum mechanical, and we just have to find a 2-level system in them, and thus we have a quantum bit, a qubit. And the good thing about those is that they can connect, they can talk to each other all at once. So they have full connectivity, but they're slow. They're in the kilohertz regime. The problem with the superconducting circuits is that they have to be close to each other to talk to each other. Then there are Rydberg atom, which is also one of the prominent platforms, or one of the platforms that is the most currently the best ones, where instead of taking charged atoms, you're taking neutral atoms and then trap them using lasers. That means that you can make this sort of grid where you can put these atoms in the grid, and then again an atom is quantum mechanical, so already you have the qubit. And once again, the problem is you need these to talk to each other, and getting this one to talk to this one is very difficult, but getting this one to talk to its neighbor is quite easy. And we want all these qubits to talk to each other. This is also very fast, somewhat fast in the megahertz regime, and the tricky part is the connectivity. All right, then the other platform, I'm not going to go through them because they're currently lagging a bit behind. You can see Xanadu has 216 photonic qubits. The problem is that they're doing light, and light is very difficult to interact with other light because light is somewhat stable. So that is a problem that they have. Intel are at 10 qubits. They're not really. It's a long time since I've seen any new research from those guys. And Microsoft is currently at 0 qubits. But it's a very interesting way, these topological qubits. If they ever get them to work, they'll be very, very stable. So as I'm stating here, it might be the next big thing once they get a big breakthrough. Yeah. So the number of qubits are actually expected to increase exponentially over the next coming years. IBM has this roadmap where they're telling they had started in 2018 with 16 qubits, and then they have increased the number of qubits each year, and they expect to have 1,000 qubits next year, and then 4,000 qubits the year after that. So currently there is a lot of movement in the quantum computing business. But having fast qubits or a lot of qubits isn't enough, because the qubit we're building at the moment are very, very bad. So they have a lot of errors in them. And actually, regular computers are also doing errors, at least many years ago. And an error can be, here you have a bit string, and then suddenly one of the bits simply changed from a 1 to a 0. That's an error. And it might happen in a classical computer as well. In modern day computers are almost perfect. There is one error every 10 years or so. So it's not really a problem. But actually more errors happens often, but we have this error correction that corrects the error, and that is usually done by saying I have 10 qubits, one of them changes, then it's probably that one that's wrong and the other 9 that's right. So that is one way of doing error correction in classical computers, and we want to do the same in quantum computers. However, this time a lot of more errors is happening. Errors are happening every second. So we need to do better computers before we can do the same kind of error correction in quantum computers. So error-free qubits are still work in progress, but it's something that we need to do, and it is hopefully something that will be developed within the next couple of years. I think we're quite close to seeing the first error-free qubit. All right, so what do we use quantum computers for? So the first and most obvious use case is quantum chemistry, because chemistry is consisting of molecules, which consist of atoms, and as we know, atoms are quantum mechanical. So therefore, it might be a good idea to start solving a molecule on a quantum computer. And actually, it turns out that, for example, discovery of new drugs is very resourceful in current computers, because first you have to figure out what molecules you want to test in the wet lab, and then you have to go make all these tests that we, for example, saw for the vaccine for the corona. It takes a lot of time and it takes a lot of money. So if we have a quantum computer, we might be able to decrease the time and resources it takes to figure out new vaccines or new drugs. Another effect could be battery development on quantum computers. And just to give an idea of what the difficulty is that here we see all the blue, that is a protein. And then this thing could be some sort of drug that has to dock into this protein. So it has to some way find its way in and sit the right place. And then you have to calculate what happens when it does that. And then maybe you have tens of thousands different molecules that you want to test into that position. And that's very resource demanding, because quantum mechanical is difficult to simulate on a regular computer. An estimate of how difficult it is that if you want to discover the next penicillin, and the penicillin is quite a large molecule, then if you want to do that on a classical computer, you would need a lot of transistors, actually more than the atoms in the observable universe. And it's difficult to make transistors out of more transistors than you have available building blocks. But on a quantum computer, you could do it with less than 300 qubits, if these qubits are perfect. So the fact that IBM has 400 qubits isn't really enough to do this already. You need perfect qubits that can talk to each other perfectly. All right, another use case could be logistics optimization. So why is this difficult? I mean, all of us has tried to order something and tried see how PostNord cannot deliver the packages. And I mean, that's a good example of why it's difficult. But if you assume that you have one ship that has to visit 10 harbors out of 100 harbors, that could be something like this in a worldview, then how many possibilities are there actually for doing this? And you have to pick the 10 harbors that gives the biggest return. and are closest to each other such that you don't spend too much time traveling around. So that gives you more than 10,000 billion probability or different combinations that you could choose from. That's a lot of combinations, and that's difficult to solve on a classical computer. But on a quantum computer, we can hopefully search for this optimal path in parallel, meaning that we can search these tens of thousands, billions combination in parallel, using something called a Grover search. So that's why we think this is a good use case for quantum computers. Another use case is finance optimization, which could be portfolio optimization or mitigating financial risk, which is also something that is increasingly important, as we see some banks are starting to collapse, and they also collapsed back in the financial crisis. So something that we need to take care of. And why is this a difficult problem? Well, assume you want to do portfolio optimization. I have 1,000 stocks and want to buy 10 stocks for maximum profit. You probably remember before I said 100 ships and 10 harbors. Now I'm saying 1,000 stocks, buy 100. It is the same problem, just bigger. So this is also a lot of combinations. And I didn't calculate this because hopefully you can see that it's a lot of combinations. But again, a quantum computer can search in parallel using Grover search. So therefore we think that financial optimization would also be suitable for quantum computing. There are other use cases, but these are the three most promising candidates probably in chronological order. I think at least quantum computing will be applied in chemistry for the first time, or when it becomes useful. All right. But there has actually been a lot of increased attention to quantum computing also in Denmark. So Kvantify was founded last year in March. And shortly after that, maybe not because of Kvantify, but shortly after that, NATO announced that quantum technology were an accelerator in Copenhagen, where they're going to research probably primarily quantum cryptography, which is something that we're not really working on in Kvantify, but also important. Something that making a new way of doing encryption using quantum computers and breaking encryption using quantum computers. And then in September, Novo Nordisk Foundation gave a lot of money to Danish research groups and Danish companies, ourselves included, to develop the first functional quantum computer. And they're actually trying to do this with photonics. I think they're not. They haven't decided on a platform yet, so they're still figuring out which platform will be the best, and then choosing one in the next couple of years. And then finally in December, actually the new government actually wrote in their foundation that the quantum area should also be developed further. All right. So Kvantify, what are we? We are actually doing software. So we're not doing any hardware quantum computers. We're just doing software for demanding computations. And that might be high performance computing or quantum computing. At the moment, we don't really care. We just want to solve the problem. We have around 30 employees, mostly PhDs, and collaborations across the EU and expanding towards a global scope. And yes, I said we were founded last year by these three guys, all with a PhD from AU. Yeah, so why even do quantum software? So quantum computers are very difficult to operate, especially now where there are very few qubits and they're very, very bad. So therefore we need specialized people to operate quantum computers. And we develop software as a service to companies that have difficult problems. And then we try to solve these problems on a classical computer and on a quantum computer. But we need to solve the classical part first to show how good do we need to be on a quantum computer in order to beat the classical computer. And that is why we're doing both high-performance computing and quantum computing. And we access quantum computers and high-performance computing using AWS and Azure, meaning that quantum computers are actually right next to the actual high-performance computing, at least on the cloud services. They might be very far apart in reality, but that way we can tailor-made solutions where they're incorporated with each other. So our approach to quantum computing would basically be that we have some Python SDK that the customer receives, and then they submit a job to our backend of a lot of classical computer and some quantum computers. in the background. Which one of these two is actually doing the job is, I guess the customer doesn't really care as long as the job is done. So that is our approach, and Søren will talk much more about the details of that.
Yes. Yes, and as Stig said, there's quite a long time until the quantum computers are, well, not a long time, but some time before we can actually employ these quantum computers in an industrial context where we can actually solve problems for users. So what can we do at Kvantify now, and why did we start, or did Kvantify start now? So we are intending to be a bridge to build from the classical to the quantum world. So I asked this DALI image generator to make an image of a bridge going from the classical to the quantum computers in the style of DALI. I'm not entirely sure where it thinks the classical and the quantum part is, but I think maybe the tentacles coming in from here is the quantum stuff, which is weird. But the point is that we also see classical high-performance computing as a tool you need to be able to solve these problems, where the quantum computing is a part of this. So we want to deliver high-performance computing. So why do we think there is a space for this already in the market? Because from what we can see from some of the potential customers we've already talked about, that many of the existing high-performance compute solutions, they are hard to use, require highly expert input in order to be used correctly. Many of them are unstable and can crash after working for weeks on many computers, and they're poorly tested. And lastly, it's really unclear how to incorporate quantum computers in traditional high-performance computing software. And since quantum computers are only available as cloud services, we feel that it's natural to deliver high-performance computing as a service where we can naturally integrate quantum computers when it makes sense to do so. So we are a software company, as Stig also pointed out. We want to check all these buzzword lists. And this also is actually a quality, because many of the problems we try to solve belong to big companies, because it's typically the large companies that have these large problems to solve. And they are often challenged at some of these parameters. So having people that knows about the frontline research in quantum computing, frontline research in algorithm discoveries, and able to iterate rapidly with continuous integration and deployment is not a given for people who use this kind of software. So these are some of the reasons why we think we can make an impact as a company. And I want to do, just to make it a little bit more concrete, so we don't only talk about the quantum castles in the sky. I'm going to go through kind of a pilot project we did with a potential customer. So as Stig pointed out, we want a problem from the customer. Maybe they want us to compute the square root of 1,000,000, really hard problem. And they send it via the API to us, and we do quantum magic stuff or high-performance compute work, and they get back the result. And so to go a little bit into detail with the actual problem we developed, it's a risk management problem from finance. And I did the calculation that Stig did not, and it's not exactly the same, but it's on the order of 2 to the 2,000 combinations. There's of course a lot of structure, so it's not all of them that are super relevant, but it is an NP-hard problem, and it's a problem where you don't know if you found the right solution. You cannot check it. And for those of you who have a hard time remembering what NP-hard is, because I always have to look it up, I'm not a computer scientist, I'm a physicist. So the space of problems that you can solve quickly, the polynomial time stuff, is probably inside the space of problems called NP, which are problems where you can check the answer in polynomial time. NP-hard problems are harder than that. So factoring is kind of on the edge here, and there's a lot of problems here that are really hard to solve, and then the really, really hard stuff is up here. So this is a problem where all bets are basically off, so you can try to solve it as well as you can, but you cannot prove anything, basically. But we can try. So the timeline of the project was that we had a numerical prototype end of March, April, just about when the company was founded. So I started around August last year, where we started developing the full continuous integration, deployment, and setting up cloud infrastructure for running the calculation, and started extensive robustness testing as well. I will get back to the later points, but we had to fix some of these robustness issues, but I'll get back to that in a while. So the tech we need to solve this problem, just to be concrete, to access quantum computers, we don't really need that yet, but we will in the future. We need Python, and we need access to Amazon Web Services, Azure, and IBM services. For the numerics and the algorithm, Python is actually a very popular language in the scientific community, so there's a huge amount of Python libraries out there to do actually also very fast numerical computation in Python, but we also see a need for stuff like C++ or Rust, because sometimes you actually do have to care about exactly how stuff is laid out in memory and how you access it. And you need C++ or Rust for that kind of thing. And the stuff we need to do is all sorts of stuff like linear algebra, Monte Carlo simulations, random stuff, all kinds of optimization. We're also looking into optimizations for the generated instructions for the quantum computer, like scheduling of instructions, machine learning, all sorts of stuff. And this requires a combination of all these things. And finally, also, we have some infrastructure we need to write. The prototype was written in Python. We probably want to use Go in the end. So these are kind of the basic tools we are going to use. And the initial architecture for what we wanted to build was, as Stig also mentioned, a Python client library, also because our customers use Python. So we have deployed this to Amazon Web Services, where we used a lot of managed services because it's easy. So we have a REST API implemented as a Lambda, like this serverless function you can execute on demand, and it communicates via S3. And then we have a step function to coordinate the execution of the actual calculation. And as you can see, once the quantum computer becomes relevant, it's fairly easy for us to plug it in here. It's not easy to write the code, but we can at least deploy it fairly straightforwardly in this, and it will be transparent for the end user. Maybe they will get a slightly higher bill, but we'll deal with that. So that's kind of the overall structure. So we set up the entire build pipeline for that. We needed to build, we needed to test it, we needed to deploy it, and we needed to distribute the client library to Azure. Because our customers are Microsoft people, so they primarily use Azure, so that was convenient. In order to do this in practice, we need to use some Python tooling. We use Poetry for managing external dependency. We use SameX stuff from C++, which I'm mostly been C++ for my professional development career. And then we use Makefiles to coordinate all this stuff, and we needed to use both Docker for the deployment, also for development, because we had some C++ dependencies that needed to be compiled in very specific ways, and also coordinate all this stuff. It worked, and that we were able to test all this stuff, and it was super slow to build, and was very brittle, and it was actually a very small code base. So this was a problem that we actually decided to deal with fairly early, because from the developer point of view, we could see this is going to be a problem, and we could see once we start rolling out with even larger problems from chemistry, in particular, this is going to be a much more bigger issue. And the reason why this was so brittle is related to the different languages and how the things depend on each other. So these are basically the software components you had from the architecture page earlier. So we have some core numerics written in C++. They have some tests. There's some Python numeric stuff as well. Has some tests. There's some services down here that also have some tests. We have some utility stuff that also has some tests, and there's some common stuff that also has some tests. Managing how these things depend on each other with Python is actually rather annoying. At least I come from C++, where I'm used to have complete control over what depends on what and what can see what. And everything is completely open in Python. And making sure that somebody over here doesn't accidentally include something from over here and gets it sent to the client is important. And making sure that when I change something in C++ and I run a Python test, is the C++ module up to date? Because in many of the tooling you can find out there, it's just it's manual step. So getting this to work consistently, also by running static type checkers for Python, was actually pretty difficult, and it was causing a lot of frustration. So even though we are a rather small company, we expect to scale, so we wanted to solve this very early. And the only thing we found that could kind of solve this annoying developer experience was a monorepo build tool. So we actually settled on using Bazel. You probably have used some of the other stuff up here. But in the end, we took the time, set it up, and it was a huge improvement. The build process was super stable. CI went down from 30 minutes to 2 minutes, including deployment. And there was just a lot of way that having this build tool in place when you have many different languages in play that encourages modularization, and you can easily cross boundaries between language in a very effective way. So you just run Bazel test and test everything in your repository, and it will fetch even the C++ compiler. And I haven't been used to seeing that kind of tooling before, and that's extremely effective for making sure that everybody has the same compiler, they get the same warnings, they get the same linter errors, they get the same of everything. Because otherwise, managing this kind of thing can be a hell, and then you get warnings on some platforms, and you don't have them on other platforms, and making sure that the code base is clean is really difficult. So that's just kind of a small story from the trenches that we also really care about delivering high-quality software. We also need to make sure we have high-quality tooling for a good developer experience. So, but getting back to the actual timeline here, the actual product, I said we had to fix some robustness issues. It turned out it was actually a very serious issue because the initial prototype seemed to work very well for a lot of cases, but it turns out that it was very much a corner case we had dug us into, because the space of this problem is really huge, so it can be difficult to find where the most difficult cases are and the most relevant cases. So we spent a lot of time figuring out what's going on, and we spent 3 months of testing and finding corner cases, and in the end we rewrote the entire thing. So the original code is completely gone, and we used a completely different technique with different optimization techniques. And here I also think, as a company, we show that we are able to, we have a fairly standard numerical algorithm we used over here, and we replaced them with something much more specialized over here. So the ability to have the knowledge to investigate all these ways of solving this problem is really what Kvantify can do. We can really dig into all the different types of algorithms for solving a problem very effectively. Because the customer who needed this, they cared most about how much money they earned. They wanted to manage the risk. So they were not software developers. They just wanted a way to better manage the risk. And maybe they could have built stuff like this, but they haven't done it for a long time. It's just something they talked about. So the fact that we can come and deliver it already shows that there's value in this kind of business. And a note about testing here also, that because, again, we want to deliver high-quality software, testing is important. But testing high-performance computing and quantum computing is actually really difficult. Because in some calculations, for example, if you are calculating how a small piece of molecule is going to dock into a protein, that calculation is maybe, I don't know, it could take weeks to run on a high-performance cluster. So how do you make sure that calculation is correct? And there are many steps in there, and it can be hard to decouple them completely because they are numerically sensitively depending on each other. So that's a challenge. Just running integration tests can be fairly expensive. Quantum computers are even worse because you cannot run your quantum program in a continuous integration pipeline, because it would be extremely expensive, and it would be very brittle because the quantum computers are also not available always. And as soon as you get to any reasonable size, we cannot even simulate them on a classical computer either. So it's completely unclear how we're going to deliver. How do you test quantum computers, algorithms for the quantum computers even? Maybe we want to use some kind of formal verification where you can automatically prove some properties of the algorithm or something. I don't know, but it's something we probably need to look into. And I think it's an interesting problem. But to summarize, we delivered something to the customer and they used it. So what happens when you do it? You send the job to the API, and the step function starts 1,500 computers with 6 cores each. So that's a lot of compute power, and it's delivered in a few seconds. So you spin up all these machines to solve a problem. We only have them for 5 minutes because you cannot get that many computers for longer than 5 minutes on Amazon. But they crunch for 5 minutes, and the results are aggregated and returned to the user in the end. And it worked beautifully. There are some limitations when you start to spin up so many processes on Amazon. For example, if you use step functions to coordinate this stuff, the payload between individual steps cannot exceed 256 kilobytes. If you have 1,500 processes that spit out a little bit of JSON, that quickly adds up to 256 kilobytes. So you need to be, so we hit some rough edges there, but I mean, it was solvable, so it was easy in the end, when you became aware that this was a problem you had to think about. In the end, we delivered the solution. The existing system they use are very approximate and ad hoc. It takes 6 hours to run, and they run it overnight and look at the results the day after. And our solution is far more accurate and much more flexible. You can tweak it and adapt it to investigate many more risk scenarios, and it runs in 5 minutes. So they will be able to do this many times a day if, I don't know, a big nation invades another country or something. Something might happen to the financial markets, which you might want to be able to take care of fairly quickly in your analysis of your risk. And they would not be able to do that before. So by delivering this kind of compute power as a service, we also increase our customers' flexibility to respond to different events. So I think it's a good business case for why does it make sense to deliver this kind of thing to customers. But I think that was I hope it became a little bit more concrete, not so many quantum castles in the sky, but actual problems that people need to have solved that we solve. And we hope the quantum computer will help us here at some point, but it's not that important really. It's just a lot of fun to build this kind of high performance compute service. And hopefully we can get some really powerful solutions when the quantum computer becomes available as well. But I think that's it. Thank you for listening.